Thank you very much. I realize that we've come to the end of a 2 weeks program, so probably everybody is getting a bit tired. Certainly I am. Let's put the clock on. Very good. So indeed, I'll be talking about a lighter subject, but therefore not less important. So for the more junior people amongst you, citations are considered to be important. Now, of course, there's nothing better than to look at somebody's papers in order to assess whether somebody's really good. But this is very difficult for people who are a little bit further away from the topic of research of this individual, particularly administrators and so on. So these kind of people tend to strive for things that are measurable. And measurable certainly means counting. So counting papers is, of course, something that is well known, but also counting citations becomes more and more relevant. And of course, you cannot dismiss the importance of citations because, you know, if somebody's been working in the field for 20 or 30 years and hardly ever anybody cites his or her work, then you may doubt about sort of the relevance of the work or certainly about the visibility of the person. On the other hand, I mean, citations tend to grow with age and you know, we also know, certainly I know, that some of my best papers are not receiving the most citations and some of my maybe poorer papers are receiving lots of citations. So it's not so clear what citations mean. And, you know, I find this a hard question. And in order to answer this question a little bit, what we would like to do is investigate data. And I've been talking so far about modeling networks in general, and I've been coming up with these caricature models, the configuration model, preferential attachment model, generalized random graphs, and we know that these models are particularly bad for basically any application that we want to get our hands upon. And this is certainly true, as I will explain in much more detail later on, for citation networks. And then the question is, what are better models for those, and what might we actually learn from that? And can we get some lessons from this to give to our administrators to say, okay, you know, citations are important, but be cautious. All right, so what are citation counts and what are we talking about? So we're talking about citation networks, and that means that the elements of your network, the nodes in your network, are papers, and you draw a directed edge between one paper and another paper when the first one cites the second one. So it's basically the in degrees that become highly relevant. The out degrees are something that you control yourself as an author. And we know that somehow there's lots of references in papers, and sometimes referees ask for more, and this is quite relevant. But this is under our own control. But we have very little control as to how many citations papers get. And the orders of magnitude between these can be vastly different. Okay, so why are citation counts hard to interpret? Well, for example, if you do them for people, how many citations people have then depends, of course, very strongly on the age that people have. If you're older, you tend to have more citations, way more. Not even clear whether this grows linearly or superlinearly in time. But worse than that, these citation counts tend to be very much dependent on the precise culture that you're in. So they're very much field dependent. And even within fields, we know that certain areas, people cite many more papers than others. And if your reference lists are much longer, then generally you will also receive more citations than others. And as I said, there are many good papers with few citations and bad papers with many citations. And in mathematics, we can understand this. Sometimes a really good paper solves a problem. But when you solve a problem, then there's not going to be much follow-up work, right? I mean, the problem is solved. So it could be a brilliant paper, but it may receive very few citations. So it's very difficult to say sort of very clearly that many citations is good and few citations is bad. I remember Joel Spencer, whom I've collaborated with a lot and who I respect a lot as a mathematician. He's a very strong mathematician. And he, at some point, jokingly said, you know, when you're young, you think that it's good to write down a conjecture and have people working on that and therefore receive citations. But when he got older, he realized that it would be much better to write down a conjecture which is wrong, because then you get way more citations. Okay, so after this sort of more jokingly, in fact, he did this at some point, not knowing it, of course, and this became a science publication, in fact, explosive percolation. And they were not quite wrong, but they were certainly not right. And this indeed created a lot of stir in the field, and in the end, another science publication by Lutz Warnke and Oliver Reardon solved the problem, and they actually showed that they were indeed wrong. Okay, so, we're scientists, and we're talking here about scientific publications, and it looks like we're screwing around a bit, right? We're doing all sorts of ad hoc things. We should actually approach these issues from a scientific perspective as well. Okay, so that's the upshot of this paper by Julia Lane in Nature already in 2010 with the brilliant title, Let's Make Science Metrics More Scientific. So a science metric is a number that you use in order to quantify whether some paper, for example, is good or not. All right, so how do you do this? Well, first of all, you should start by looking at the data. If you want to say anything about the real world, you've got to know what the real world behaves like. So we look at data, and we actually have access to the Web of Science data set. So probably many of you have used Web of Science in order to find publications. It doesn't cover everything, and certainly in the fields such as computer science, it's a very poor representative of the field. But in many other fields, it actually covers quite a bit. And in general, it has about 40 million papers in total, with about 500 million citations starting in 1980. And we got access to that enormous data set through a collaboration with CWTS in Leiden, which is both a company as well as a part of science, a scientific institute in Leiden University. And they're really serious about investigating impact of science, impact of scientists, and so on. And they really want to do a good job. And it's hard. It's hard. What kind of problems would we like to look at? Well, for example, how many papers do citations receive? And what is the variability in these citation counts? How long does it take for papers to receive citations? Initially, it takes a bit of time before your work starts to be known. And in fact, you start talking about the paper when it's almost done, and then you try to publish it. It's published at some point. For other people to start picking it up, it takes a long time, certainly in math. Generally in mathematics, projects take a long time. They can take up to 10 years. Now, of course, there's a high amount of variability in different scientific domains, and therefore it's actually useful to look at some specific domains. So we looked at three, but actually my student, I should have mentioned this is joint work with a former student, Alessandro Garavaglia, who graduated last January, and also with Nelly Litvak from part of it and Gerhard Böginger. So Alessandro looked at many more fields and basically drew the same conclusions. Okay, so what sort of data are we looking at? Well, let's start by the very simplest thing. How many papers are there in these different fields? And, so far I've been showing you lots of log-log plots. This is not a log-log plot, this is a log plot. So you only take one logarithm, and you take a logarithm in the number here, but not in time. And then you see something which sort of looks a little bit like a straight line again. And now this does not mean that it's a power law, but it means exponential growth. Okay, so that basically means that as time progresses, the number of papers grows exponentially. So if you were wondering why you were feeling so busy, well, that's probably the reason, because I doubt that the number of scientists is actually growing exponentially at the same time. Now, of course, it could be that the coverage of Web of Science has increased in that same time period. That could also be a cause of why this exponential growth appears. But I think there's more at hand. I actually think that people write more and more papers these days than they did in the old days. And this exponential growth has been going on for a very long time. It was already observed by Derek de Solla Price, and he is one of the top people in this field. In his 1963 book, well, that's prehistoric, basically, and it's called Little Science, Big Science. Okay, so exponential growth of the number of papers. And then you may wonder, what is the distribution of the number of citations of these papers? Okay, so we're looking here at the in degree in the citation network, and this is for the three different fields in three different colors. And what you will notice is that the amount of variability is humongous. So the best cited papers have of the order 1,000 and sometimes even 10,000 of citations to them. They are somewhere here in the back. They're very rare, but they are there. And at least from some perspectives, there seem to be straight line-ish parts in these graphs. The slope may be slightly different, and we know that this really is a log-log plot. if you were to have a straight line and you would have power laws in these data sets. So there appear to be heavy-tailed phenomena in the citation distributions of the different papers. All right, but you can also look at this in a more dynamic perspective. So take a cohort of papers from 1 year. In this case, it's 1984 for no particular reason. And then follow the citation distribution of that cohort over time. Now, of course, we know that papers can only get more citations, and once a citation is there, it will always remain on being there. This is not true for many other networks. This is actually a big advantage of this network. Okay? So what happens when you see somehow time change? And here we're looking from 1984 all the way to 2012. That's actually a pretty long time period. And what you see is that the citation distribution moves up. That, of course, has to happen because papers will start receiving more and more citations. But what you also see is that if you were to try to fit a slope to this, then even this slope is moving up. So we call this a dynamic power law. Now, it's not extremely convincing because, you know, how straight line-ish are these things? Well, not really a lot. So you have to be a bit careful here. So this is for probability and statistics. That's what PS means. And here you see the same thing for biomedical technology. And here you could argue that somehow the straight line-ish piece here becomes longer and longer, and maybe as time progresses, in the end, it will become this straight line-ish thing that we see in the end. Okay? So if at all there are power laws, they should certainly change over time. So somehow the heavy-tailed phenomena should become thicker if you look at a fixed cohort of papers as time progresses. So we call these dynamic power laws. Now, there's many ways how you can visualize the data in somehow the dynamics of the network in a good way. This is another way how you could look at it. You can just take a random sample of a few papers, 20 papers from 1980 in the different fields, and see how the citations of these papers move. Well, of course, the citations go up, and what you see is that there's a high amount of variability. There typically tends to be 1 or 2 papers that get lots of citations, whereas the majority actually stops on receiving citations relatively quickly. So here, this bottom one may have received 2 citations or so. That's very little, whereas the top one here has above 60 of them. Now, they all seem to end up in the rightmost corner, but that's just because of the way how they've been plotted. It basically is cut off here at the rightmost corner at the highest value. Okay, so what you see is that there's a huge amount of variability. What you also see is that most of the papers actually stop receiving citations at some point, but the time at which this occurs is random and depends on the precise paper, and particularly the papers that receive lots of citations, for them it occurs much later. And maybe not at all. It's not so clear whether this will ever stop receiving citations. Of course, it's very difficult to look into the future. So these things are pretty variable, even in their dynamics. Now, what you can also do is look at cohorts of papers and see where these citations are occurring in the future. So this, again, is a cohort of papers. Here we're looking at 4 of them, a cohort of papers from 1984, 1987, 1990, and 1993. And we look at the average number of citations of these papers as time progresses. So these are 20 years. So the cohorts have been chosen in such a way that we have this full window. And what you see is that initially they have very few citations, as you would expect. Somehow the news hasn't gotten out yet, and the follow-up work is not there yet. And then it goes up. And then slowly it becomes less. And it really depends on the field, on how quickly this becomes less. So probability and statistics are part of mathematics. Mathematics tends to be a very slow field. So citations will basically propagate for a pretty long time to come. Whereas electrical engineering is a more hip field, where somehow problems become very timely, a lot of people work on them, and then after some time they're being forgotten, and that means that actually the science changes more rapidly and citations will be lost more quickly in time. And the same thing is true for biomedical technology. But the shape of these pictures are not that different. So the time horizons are quite different. And if you were to rescale them in an appropriate way, in such a way that these pictures look a bit alike, then what you see is that at least the shape of these curves looks fairly similar. Now this is another perspective. So before I was looking at a fixed bunch of papers and looking at when they receive their citations. You can also look at the papers and look at how old the references are. Basically the same data, but shown in a different way. And here you can look at the proportion of papers, so it's nicely, these are nice probability distributions. You can look at the proportion of references in papers that are up to 5 years, 10 years, 15, 20 years ago. And these pictures look quite similar for probability and statistics for the papers in different batches. Now these batches are in 2004, 2007, 2011, and 2014. So somehow it's fairly time homogeneous how old the papers are that we cite. That doesn't change dramatically over time. Yes, we use Web of Science. Publication date. Web of Science does not look at the archive. So it may make a big difference. But not every field has archive. So it becomes more difficult to investigate what to use.
After publication date is peak.
No, that's not what this says. This says that the most papers that are 5 years old are being cited in papers. Yeah. That's not exactly the same thing, because the other one that was this one. Yeah. And here indeed also, well, the peak may be a little bit earlier, 3 years. So the majority of citations, at least in this field, in electrical engineering, you get after 3 years. But this says that the peak of the references in papers is 5 years old. Good question. Now here you see the same picture, but then for biomedical technology. And that actually, again, it doesn't look that different. So the shape is fairly similar. Also, there is not much change over time. It is rescaled in the axis. That's because biomedical technology is a field that moves more quickly than mathematics. So it's a rescaling done in time. Well, that's basically it. And it's claimed that actually this distribution is roughly log normal. And it certainly looks like it. So I have it here with a question mark. Now that's the final picture that I would like to draw about citation networks is how citations accumulate over time. Can we do some sort of a prediction? And the answer to that is yes. The best possible prediction we can do, let's say that we've seen a paper for 10 years. Can we predict how many citations it will get, let's say in year 11? Well, just take a multiple of the number of citations it has had, up to 10 years. So basically the amount of increase of citations is roughly linear in time. So that's what we see here. These dots are averages of numbers of citations in the next year. And this here is the number of citations up to that point. And this is for 3 time periods later on. So it's about the papers published in 1984, again, that same cohort. But then you look at the number of citations it had at in year, up to year 1993, and then in the year itself, 1993. So it's the prediction that the citations grow linearly is not so bad.
This is for an aggregate, right?
An aggregate.
This is for a collection of papers. You're looking
yes.
at the total number of citations.
Yes, I think so. But it's rather finely aggregated because you aggregate it on the basis of the number of citations of that cohort up to the time point that you're looking at. So you're looking at all the papers, for example, here that have received 100 citations up to the year 1993, and then you average out how many citations they will get in 1993. And that's what the dots mean. Okay? All right, so what is the conclusion when we look at this data so far? Well, the first maybe worrying conclusion is that the number of papers grows almost exponentially in time, that the citations per paper vary rather dramatically, that the citation counts follow approximate power law distributions with the exponent changing over time if you look at it dynamically, A paper stopped receiving citations after some time, but this time is highly variable, depends on the particular paper that you look at, and that the age of cited papers looks roughly log normal. And it seems to be a reasonable prediction that citations grow almost linearly in time, given the past. Okay? So what we would like to do is build a model that has similar characteristics. And that's not entirely trivial, because first of all, this is a highly dynamic network, so we have to model in the dynamics. And we've seen a model of a dynamic network, that's the preferential attachment model, but that clearly doesn't satisfy any of these properties, basically. Okay, so we'll have to adapt it. So how are we going to do that? Well, modeling networks, we've already seen lots of this, so I'll do this very briefly. Static models, Ehlers-Danlos random graph or other inhomogeneous random graphs, configuration model, but we certainly have to look at dynamic models here, because we're interested in the dynamics over time. And that means that the graph has an evolving number of elements, and we've seen a model of that nature, that's the preferential attachment model. And of course, citation networks are highly dynamic. And we need to focus therefore on dynamic models. And the nice thing about citation networks is that they really grow in time. So in many settings where somehow the evolution of a network is dynamic, it not only grows, but it can also have vertices disappearing. So for example, in Facebook, there are lots of people who are saying up their Facebook account, and therefore these vertices will go away. And that's something that is not present in citation networks, and that actually makes it slightly easier to deal with. All right, so the model for a dynamic network that has been attracting a lot of attention in the literature so far is the preferential attachment model. And by the way, this paper is actually one of these papers that is very far into the right of the citation counts. I was writing 31,000 here, that's an old count. I did it again before my course, and then it was 34,000, so it's still growing. Okay? And the philosophy behind this is very easy and maybe very appropriate to citation networks, because a paper that is cited very often is more likely to be cited somewhere else. Why? Well, you know, if I read a paper, I sometimes also look at the citations or the references in the paper, and if I'm bound to see that reference very often, I may be more likely to have a look at the paper and therefore more likely to actually cite that paper. Okay? So there is some preference in the dynamics of citations is pretty obvious. How it comes out is not so clear. And in this model, what happens is that the network grows, let's say, linearly in time. At every time moment, a new vertex comes in, it has a few edges, and it attaches that to old vertices that are there, proportionally to a function of time and the vertex, that is basically the degree plus a little constant. And as I've tried to explain during the course, this gives rise to power law degree sequences, and you see a degree distribution in a simulation that looks very much like an IID sequence with a similar power law. And this is not exactly the model by Albert and Barabasi, because I've added this little constant, and the reason why I've done that is that it gives more flexibility in the precise choice of the power law exponent. You see that this delta here enters here in a linear way. So by varying this delta, we can actually vary the power law. Larger delta means thinner degrees, smaller delta means heavier degrees. And there's something to be said for that, because, you know, if delta is very negative, then the values, the vertices that have relatively small degree are going to suffer a lot. But if you already have degree 10,000 and 5 is being subtracted from you, you don't notice it at all. So it has a stronger tendency to push towards vertices of very high degree. So that's the reason why the behavior on delta is positive, in fact it grows linearly with this delta. All right, so this is a nice model. It has attracted a lot of attention, but is it good for citation networks? Well, clearly not. It has several problematic features. So first of all, I was saying that this is the rich get rich model, but I've already explained during my course that in fact, a better word for it is the old get rich model, because the vertices that have very high degree are all the old vertices. Now this is certainly something that is not true in citation networks, because, you know, you can have these papers that come into the game, for example this one in 1999, that all of a sudden become the stars in terms of citations and start receiving lots and lots and lots of citations. This is never going to happen in a preferential attachment model. Okay? So that's one problem, the old get richer problem. And one way to resolve this is by introducing fitnesses. So rather than looking at it this way, you multiply this by a random variable, and if that random variable is extremely big, then you're much more likely to be attaching to the particular vertex that you're having in mind. And because you're multiplying, if you happen to come in late in the game, but still have a huge fitness, then you're still going to attract lots of edges, and therefore get a pretty high degree. So that's one way of solving this particular problem. There's a more trivial problem. I mean, the size of the network in a preferential attachment model grows linearly and not exponentially. And in fact, this is a nice property, because what you can do is you can embed these preferential attachment models in continuous time. That's actually a very cool way to investigate them even. So this is also a way to prove properties about their degree distributions. And the reason is that what happens here is that these graphs are closely related to continuous time branching processes. And we all know that branching processes, if they're supercritical, they tend to grow exponentially. And the same thing is true here. So these models immediately grow exponentially as these citation networks. So this embedding in continuous time, on the one hand, it's convenient in order to be able to prove results. On the other hand, it actually turns out to be closer to reality. So that's nice. We're killing two birds with one stone. Also, it allows us to actually use powerful tools from continuous time branching processes, and there have been a few influential papers and also a book by the Swedes, as we sometimes say, by Peter Jagers and Ulle Nerman, where they do very general settings of these continuous time branching processes and prove all sorts of very beautiful properties for them. For example, their exponential growth. And this has been used for regular preferential attachment models, particularly in the tree setting, where everybody comes in with one edge, by Rudas, Todt and Valko, and also by Krishna Athreya and some of his collaborators. All right, so we've discussed two problems here. Preferential attachment models grow linearly and not exponentially. This is the fix. We've talked about the fact that the preferential attachment model has an all-get-rich phenomenon that we don't see in citation networks. Here's the fix. Random fitnesses, and we also see that in the preferential attachment models, the degrees go up. So the degree of every vertex tends to infinity almost surely. That's also not something that we see in these citation networks, because citations stop at a certain moment for particular papers. So we need to build in that mechanism as well, and that comes into a certain aging effect that we put into the model. So if we put all of these things together, what we're left with is a model that evolves in continuous time, where there's a preferential attachment mechanism still available, but it's being pre-multiplied by a random fitness, somehow making the degree distributions more variable even. And it's post-multiplied by an aging effect. So if this, if a vertex V has been born at time S, then we post-multiply its rate of growth by a function that depends on t minus s. And we'll be assuming very little about this function, but just that it's integrable. And the fact that this is integrable basically means that over the whole evolution of time, if a vertex is born, it will receive a finite number of citations, but that finite number is a random variable. Okay, that's what it means. So here in different dots, eta of V is the fitness of V. We take them to be IID, and that this is the reason for it. Citation counts become highly variable. G is an integrable aging function. Vertices receive a finite number of citations in their lifetime, ever. The degree is being kept track of, and if the degree is larger, you're more likely to get a child. That's this effect. And this delta is a parameter that is that allows you to fine-tune the precise characteristics of your degree distribution. Now we're going to be doing this in a setting where we're dealing with trees. And the reason for this is that then we can use the powerful methodology of continuous time branching processes. I have no doubt that anything that I'm going to be saying is going to be true if you have a variable number of references per incoming node, but it's just that it becomes much more difficult. That's at least what we see in preferential attachment models. The setting where m is 1 versus the setting where m is greater than or equal to 2 is not that different. So let's start with this very simple model. Okay, well, here's one result. So we're going to be looking at the number of individuals in the system, so the total number of papers at time t. And what we see is that this grows exponentially with a certain rate alpha, and then there's a random variable that is multiplied by this. You should really think about this in a very similar way as in discrete branching processes. If you look at the number of individuals in the nth generation, this grows like a power of n, mu to the power, where mu is the mean offspring distribution, but there's a random variable multiplying that. It's very similar here. And then if you look at the proportion of vertices at time t that have citation count k, so degree k, that actually converges to some limiting probability. This probability is actually a deterministic thing. So if I sample a paper uniformly at random, or an individual uniformly at random from my model, it will, with probability pk, have degree k. And therefore this asymptotic degree distribution should be what characterizes the differences in my model. So there's very many different behaviors that this pk can have, depending on the precise setting that you're in. So I'll just do this by pictures. But many of these pictures can actually be made rigorous. Okay, so this is the picture, again a log-log plot, and what you see is that there's one here that drops very dramatically. That's actually corresponding to a pk that is exponential, that has an exponential tail. And this is when you just have aging and no fitness. So when you have introduced aging and no fitness, it turns out that your degree distribution becomes thin-tailed with an exponential tail. So you somehow need something to counteract the fact that this aging will make it sure that you're not going to be receiving many citations. And the way to counteract it is precisely this fitness. And if you have a high amount of fitness variation, then it could still be that the vertices with very high fitness can still receive lots of citation, even though you have an integrable aging.
What distribution you give to fitness?
I'll get to that. So that's what we see here in the green picture, aging with a fitness process, and we were taking the fitnesses to be exponential distribution. And then it turns out that your degree distribution again has a power law. And the red thing is the thing that we've seen before. It's called here the stationary process. This is just a regular preferential attachment model, where you don't have any fitnesses and you don't have any aging, and you're just doing it according to this. And then what you see is that also then there is a power law. So the way how you should think about this is that the aging actually kills the heavy-tailed phenomenon, and in order to restore it, you need to have an amount of fitness that is highly variable, and then you're going to get your power laws back. And in fact, that's if and only if you need to have at least an exponential tail, otherwise you're not going to have heavy-tailed degree distribution, power law degree distributions.
What if you have fat tail distribution there?
What if you have?
Fat tail distribution.
Makes no difference. You're still going to get power law degree distributions. Yeah. So there's some flexibility in these fitnesses. As long as you have at least an exponential tail, then you're going to see this power law. But of course, the power law exponent depends sensitively on the precise parameters of the model. There's also a high amount of universality in terms of the precise shape of my function g. I haven't said anything about this, but basically the only thing that matters is that it's integrable. We already get a dynamic power law here. If it would not be integrable. We didn't think about that because somehow our thinking was very much shaped by these citation networks, and our thinking was, it's probably the best dogma or paradigm to think that every paper is going to receive a finite number of citations eventually. Of course, there's no, this is a modeling paradigm.
So do you have Einstein's paper?
Yes. And you think that if time tends to infinity, they would receive an infinite number of citations? Maybe they do. Maybe the paper by Albert and Barabasi as well. I don't know. A very good question. We didn't think about that, but then you would need much more sort of modeling assumptions as well. So it's an interesting question. I don't know what the precise effect of that would be. Yeah, in general they do. Yes, but Peter's point is that some papers actually may not. And that's not taken into account here. And he was pointing to Einstein's papers, and maybe he's right. So this was the question that Peter was asking for. What about papers from a certain cohort? And how is their citation counts, how are they changing over time? So that's what we've been measuring here. And of course, if you start simulating, it's much easier to do this compared to really counting it in Web of Science. So what we did here was, for certain time units, whatever they mean, we looked at the citation counts of a certain block of papers that was born in a certain time period. And what you see is that as time progresses, of course, they receive more and more citations, and the way how they receive more and more citations is very similar to the pictures that I was drawing before here. Actually, it's difficult to see the difference between the two. Oh, I've gone too far. Now, we've done it for far longer as well, and then you see that this eventually will go to some limiting distribution. And that basically means that if you let time run to infinity, and you look at the papers from 1984, then they will probably get some sort of a limiting distribution for the number of citations they have. So what we see is that, at least sort of from a simulation perspective, and sometimes from a mathematical perspective, we can analyze this network, this tree network. And what we see is that there's a reasonable qualitative comparison. I'm not doing anything quantitatively. I'm not trying to estimate fitness distributions or aging functions or whatever. But at least at a qualitative level, there is a reasonable comparison between the data and the model, in the sense that both the model and the data have an exponential growth. Both the model and the data seem to have an integrable aging, at least for typical papers, excluding Einstein's papers. There's a high amount of variability in terms of how many citations papers get, and this is being modeled by this high variable fitnesses. And we have rigorous results in the tree case, when every paper comes in with exactly one reference. That's basically what it means. Exponential growth is the typical behavior, because we're mapping to continuous time branching processes. And power laws with aging and fitness only, precisely when the fitness distribution has at most an exponential tail, not thinner than that. All right, any questions about this? Yes? Excellent question. This is not at all clear. So we have a project ongoing with a machine learner from Twente, and we're trying to use this. So what we're trying to do is to have different classes of models, simulate them, and then try sort of have a test set and a later set, and try to have a machine learning algorithm decide which of the different classes of models it is. Okay, that you could do, certainly on the basis of your model, and then you could feed in your data into this machine learning algorithm, and it will give you some probabilities of what it believes to be the most likely model it came from. That may allow you to distinguish between different models. So that could be a way to do it. That's a much weaker approach than estimation, and estimation is totally hopeless. And in fact, there's a big problem in the Web of Science data set. I mean, we've been trying to do this sort of in a more rigorous statistical way, but one of the problems is that the Web of Science database was started up from 1980. So there's really something happening in 1980, and there are some papers that are there that are earlier, that are older. Einstein's papers are probably there. So it has some sort of a backlog of these earlier papers, but it really became more and more complete after 1980. So there's this change in time that will actually make it very difficult to compare the data set to the model. In fact, the model will be wrong just because of this. But is this a problem of the citations, or is it a problem of your data set? I would say that it's a problem of your data set. But we find it very difficult to go around that perspective. So estimation and so on are very difficult. So that's why we're trying this machine learning approach instead. Very good question. Other questions?
Are you trying to somehow incorporate the quality of citation?
No, that we haven't thought about. I mean, the PhD student is done. So then, of course, you start wondering what you should do. Well, what I would think would be much more interesting is to really take the step to people. We haven't done that. We're really here at the level of citations. So if you would want to do that, you have to bring the people back into the game and go from the citations of papers to the authors, and also try to say something about what makes somebody a good author. And can you say something, for example, about the evolution of the H-index and these kind of things, trying to understand whether these would be good metrics.
Journal maybe one. Quality of journal maybe one.
Yes, so you're trying to ask another question which is highly relevant. So I'm just taking my fitnesses to be IID. So funding agencies, for example, would love to know whether the fitnesses of people who get funds from them, whether the papers that they write have higher fitnesses than the average one. So if you would be able to do some sort of a statistical analysis, maybe multiple regression or so, to say something about specific sets of papers and their fitnesses compared to other sets of papers, but this to me strikes me as a very difficult problem because it's even very unclear how you should estimate the fitness of one paper. So how the hell are you going to do this with many, many papers? But this is really what people would like to know, certainly in the publishing world and also in the science foundations. Yes, and we know that this happens. There's even people who actually launch their own journal and then tell the authors in that journal to cite certain papers in that journal. So there's lots of fishy business going on in science. But indeed, I mean, what you're asking about, more general, is can you somehow detect fraud or anomalous behavior in networks? And this is a very lively question. I know very little about it, but this is indeed a very good point. Precisely. Yeah, so part of this is being accommodated in many of these citation counts because you can exclude self-citations. But of course you're going a little bit further and you're probably quite right that actually communities may actually collaborate on receiving more citations. And this is precisely the reason why you have to be really careful in counting citations. So let's go to the final topic in my last few minutes, because we're actually often interested in trying to quantify what makes a paper important. And what people tend to do is just look at the number of citations. And my argument would be that this is actually wrong. You should not barely simply count citations. You should somehow weigh them. I mean, it makes much more sense for me. I mean, it's much more valuable for me when I receive a citation from Peter than, you know, from maybe one of my own master students who writes up his thesis work. I can expect this master student to cite me because I've given him the problem, so it's probably relevant for me. So you have to weigh the citations in a different way. And the question, of course, is how should you do that? Because now I'm sort of making it into a problem where I'm saying, you know, actually important papers should count much more for my importance. But then again, how do we decide that somebody is important? Right? It becomes a circular problem. But there is a way around this, and this is called PageRank. And PageRank is a very good way of classifying who's important in a network. It was invented by Brin and Page. Who does not know who Brin and Page are? You don't? Founders of Google. And in fact, they founded Google precisely because of this algorithm. And those of us who've been around in searching on the World Wide Web before Google and after Google know that, you know, before Google you would get a total mess when you would be asking for somebody. It was working much more like a telephone book. And afterwards, somehow there was really some sort of an order in the answers that you would get. And PageRank was doing this. Now, of course, PageRank is not exactly what Google is using now. In fact, it's highly classified what they're using. But let me try to explain what they do. Okay, so PageRank is simply the stationary distribution of a certain random walk on the graph. And it's a very simple random walk. It's a random walk that flips a coin and then decides whether it's going to be moving to one of the neighbors uniformly at random or whether it restarts completely. And when it restarts from a uniform location. This restart is very, very important. That's measured by this 1 minus c here. And it basically makes sure that somehow this random walk mixes very quickly. Because all the time you have a positive probability of jumping anywhere. And that actually means that you can look at this stationary distribution that's well defined. And it's useful to actually renormalize that PageRank, so multiply it by n, because then at least the average value over the network will be exactly equal to 1. Okay? Whereas this stationary distribution, as the graph becomes bigger and bigger, vanishes. Okay? All right, so that's PageRank, very quickly. And the funny thing that you see in PageRank is that there's a high amount of similarities between the in degrees and the citation counts, the citation distribution or the PageRank distribution. The question is why this is true. Now this may seem to you now that actually it's the same papers that are very high up in the game, but that's actually not necessarily true. You can have a very high PageRank, not because you have a very high in degree, but rather because there's a very influential paper with a very high PageRank that is referring to you. okay? So it takes much more of the network into account. All right, there's a lot of work about this. You can study this using local weak convergence, and as it turns out, if your graph converges locally weakly, then it turns out that the PageRank, this graph normalized PageRank distribution, converges along with it. So it basically says that this PageRank distribution is a local property, but it's not a property of your immediate neighborhood. Citation counts are a property of your immediate neighborhood. Here you really have to look a little bit further than that. And therefore, I think it's a better measure for measuring importance. And there's still a lot of work to be done in order to understand how this would work on citation networks. And I'm over time, so let's stop here.
Questions? Look like you had the same order on the same slope.
Yes, they have the same slope. Yeah.
Something that comes out from the theorem as well?
No, not from this theorem. So, but there is work in that direction. This is called the power law hypothesis. This is believed to be true not just, I mean, here we're doing it for citation networks, but it was actually observed for the World Wide Web first. That the in degree and the PageRank distribution have the same power laws. They have a different intercept, right? That's what you see here. They're shifted compared to one another. And you can predict that. And there's been some work in this direction for some directed graphs, directed configuration model, directed generalized random graph, and these kind of things in order to explain this. So for these models, they can actually explain that in these models, in fact, this effect occurs. But often the problem of convergence of this PageRank was treated simultaneously with the power law hypothesis. And we decided to split the two problems. First, prove that actually very generally, if your network converges in the local weak convergence topology, then actually the PageRank distribution will converge as well to something that you can compute on the limit. That might give you an easier way to get to this power law hypothesis and prove indeed that these two slopes are very similar in a much more general setting than very specific models. That was our aim. Good question. Ouch. That's of course always a very dangerous question. I would say, you know, still look at the papers. Look at the papers, look at the citations, look at the number of papers, look at the journals, look at, you know, it's a very high dimensional space. It's too easy to expect that one number, such as the H index, is going to tell you everything about the scientist. And in fact, you may even want to talk to the person because you also want to know whether he or she is going to be a good colleague. That's not measured anywhere.
Yes, that's
So
pretty important, frankly.
that is actually very important. So that's the best advice I can give, I think.
Let's thank Remco for a very fascinating time.
So we've come to the end of the program. It's been 2 weeks. I've only seen one of them, but this was extremely exciting. I've loved it. So this is the time, I think, to also thank all the organizers. I hope that I can get them out of the top of my head. Devavrat, Piyush is still here. Yes, thank you very much. Kavita, Sandeep, Vivek. Is that everything? Okay, thank you very much for all your work on this.